Today we're going to be reviewing Unit 4, Science, Chapter 4, Physical Science, which technically is our last chapter with the book. Remember, you can follow along with your GED Test Prep Plus 2020 Kaplan book. You can pause and rewind at any time that you like. So why don't we go ahead and let's get started with our last chapter in the book. Welcome back. As always, please remember that we are following along with the GED Test Prep Plus 2020 book. You can look down below for different places where you can go ahead and order it. During this video, we are going to go over Unit 4, Science, Chapter 3, Earth and Space Science, Lessons 1 through 5. We will be starting on page 538. Lesson 1, Atoms and Molecules. In the previous chapter, we briefly touched the topic of atoms. Remember that according to the Big Bang Theory, the universe formed from an atom. Well, in this lesson, we are going to learn more about the composition of an atom. When a group of atoms are combined, they form matter. An atom is the smallest unit of matter that can be combined chemically with other matter and that cannot be broken down into smaller particles by chemical means. Atoms are made of subatomic particles. Some of the major ones include protons, neutrons, and electrons. Protons are particles with a positive charge. Neutrons are particles with no charge. When you combine a proton with a neutron, they form a nucleus of all atoms except hydrogen, which has just one proton in its nucleus. Electrons are particles with negative charge. Electrons orbit the nucleus of an atom. When an atom has an equal number of protons and electrons, it is electrically neutral. When the atom gains or loses electrons, it becomes negatively charged or a positively charged ion. Matter can be classified into elements, compounds, and mixtures. Elements are substances that are not able to be broken down with other substances. They are made of a single type of atom. Some good examples are gold, iron, hydrogen, sodium, oxygen, and carbon. Each of these elements has a chemical symbol, as you can see in the diagram on the right. These symbols might look familiar. That's because these are elements taken out of the periodic table. Matter's second classification is compounds. In this stage, substances are formed from two or more elements chemically combined in a definite proportion. Compounds also have properties that differ from the properties of elements. For example, water in this composition is a liquid compound. However, when each element is by itself, they are both considered gases. Compounds are represented as a chemical formula. For example, water is written as H2O, meaning that water has two hydrogen atoms and one oxygen atom. When matter is classified as a mixture, it means that two or more substances combine, but they are able to keep their properties. A perfect example is salt water. Salt water is a mixture of sodium and chloride. This means that salt water is formed when sodium atoms interact with chlorine atoms. It also means that for every one sodium atom present, there is exactly one chlorine atom present as well. We learned about the different classifications of matter and how the composition changes in each classification. Let's now take a look at what happens when elements combine to form molecules or ionic compounds. Molecules are held together by bonds. So bonds, think of it as glue. There are two types of bonds, covalent and ionic. Let's take a look at covalent bond. In a covalent bond, the molecules are formed between atoms by the sharing of electrons. So both atoms need to contribute one electron each. So there's no time to be selfish in this case. So let's look at an example. Water. We know that water is made of two atoms, hydrogen and oxygen. The atoms are being held together by covalent bonds because oxygen is sharing an electron with hydrogen and vice versa, making a pair of electrons. In an ionic bond, atoms can gain or lose electrons to become ions. Let's look at an example. Sodium chloride, or salt as we all know it. Sodium loses one electron, but it's not lost. It was just transferred to chlorine. When an atom loses an electron, it becomes an ion. So in this case, sodium became sodium ion. And because the electron that sodium lost was transferred to chlorine, chlorine is now an ion too, because it gained an electron, therefore becoming a chloride ion. Because opposites attract, sodium ion, which has a positive charge, and chloride ion has a negative charge, they combine to form or to become sodium chloride or salt. Now that we have finished our first lesson, let's move on to practice 1, found on page 553. Let's move on to practice 1. We're going to complete the questions 1 and 2. As it is customary, during this point in time, I would like you to pause the video and take a minute to complete questions 1 and 2 on your own. And when you are ready to continue or review them together, just go ahead and press play. So for questions 1 and 2, you're going to use the text on page 552 to answer them. Welcome back. So let's go ahead and start with question 1. Question 1 reads, sodium is represented by the chemical symbol Na, and chlorine is represented by the chemical symbol Cl. According to the text and the diagram on page 552, what happens when sodium chloride forms? Okay, so remember that we just did this in the previous couple slides. We talked about ionic bonds. So let's look at our options and see if one of those is familiar. Option A, the sodium atom loses an electron, becoming positively charged, and the chlorine atom gains an electron, becoming negatively charged. The sodium atom gains an electron, becoming negatively charged, and the chlorine atom loses an electron, becoming positively charged. Or option C, the sodium atom gains an electron, becoming positively charged, and the chlorine atom loses an electron, becoming negatively charged. Or option D, the sodium and chlorine atoms share a pair of electrons, becoming ions and forming a covalent bond. So option D is out because we know that they are not sharing a pair of electrons, and sodium chloride is an ionic bond. So let's go on and take a look at the other examples. So we already know that when sodium is combined with chlorine, sodium loses an electron in order to transfer it over to chlorine. And then once one loses and the other gains, so therefore they become ions. The other thing that happens is when one loses an electron is that they become positive or negative. In this case, sodium becomes positively charged and chlorine becomes negatively charged, therefore forming a chemical attraction between each other. So given what we know, and given the covalent bond and the ionic bond by definition, and what we learned what happens when sodium and chloride combine, we know that the answer is A. The sodium atom loses an electron, becoming positively charged, and the chlorine atom gains an electron, becoming negatively charged. Let's look at question 2. Water is composed of 2 atoms of hydrogen and 1 atom of oxygen and has the formula H2O. Glucose, a simple sugar, consists of 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. Which of the following is the chemical formula for glucose? So here we have different options. So we know that oxygen is H2O because there's 2 atoms of hydrogen and 1 atom of oxygen. So let's look at our options. Option A is CHO. Option B is 6 atoms of something. We don't know what, but there's 6 atoms of something, 12 atoms of carbon, 6 atoms of hydrogen, and 1 atom of oxygen. Well, that doesn't seem right because you need 6 atoms of oxygen, and we really we don't know what 6 atoms of nothing is compared to. So that's not a possible answer. And option A is not possible because they are not contributing any atoms from what glucose is composed of. Now let's look at option C. C has 6 atoms of carbon, hydrogen, 12 atoms of hydrogen, and oxygen, 6 atoms of oxygen. It seems correct, right? But hold on, let's take a look at our last option. Have 6 atoms of carbon, 12 atoms of oxygen, and 6 atoms of oxygen. So which one is correct? C or D? Well, let's go back to our formula they gave us for water. H2O. Do you see those little itty bitty numbers right after the H? So those are the atoms that hydrogen is contributing in order to make water. So whenever we write a chemical formula for some sort of combined element, we have to put in the number of how many atoms it consists of at the bottom. By doing so, we know that the answer is going to be D. At this time, pause the video, complete practice questions 3 through 5, and click play when you are ready to continue. Let's move on to lesson 2, properties and states of matter. In this lesson, we will be focusing on matter. What is matter? Remember that the universe was created from matter, so it must be important. So matter is anything that has mass and takes up space. Mass is the amount of matter an object contains. It could be a light object or a heavy object. Mass does not change regardless of where someone or something is. So think of it as volume. Remember from previous lessons, volume is the amount an object is able to hold. Nothing compared to weight. Weight is a measure of gravitational force exerted on an object. So in other words, the force of gravity on an object. For example, a human being, their mass will not change despite of the location where we are. We could be on the moon or we could be on Earth. that will stay the same. However, our weight will definitely change. And the weight will change because it is directly related to the force of gravity. So if we were on the moon or any other planet, our weight will change based on the gravitational pull related to that planet itself. The moon's gravitational pull is less than that of Earth, therefore, we would weigh so much less on the moon than we do here. There are three states of matter: solids, liquids, and gases. Solids have a definite shape and volume because the molecules that form it are not able to move freely. Some solids, such as minerals, their molecules form a pattern called a crystal. Matter, in a liquid format, has definite volume but no shape. The molecules are able to move freely, and because they have no definite shape, they are able to adjust to the shape of its container. Matter in its last state is gases. In this state, matter has no shape or volume. The molecules are always in motion and there is no attraction to each other. Remember that matter has three states: solids, liquids, and gases. The states of matter can be changed by adding or removing heat energy. Let's see what happens when we add and remove heat to matter at different states. When heat is added in a solid state, it melts. The motion of its molecules increases until the bond breaks and the molecules are able to move around freely. The temperature when a solid melts is called its melting point. When heat is applied to a liquid, it boils and evaporates, turning the liquid into gas as the motion of its molecules increases. The temperatures at which a liquid becomes a gas is called a boiling point. When heat is removed from a gas, the molecules slow down and it turns into liquid. The temperatures at which a gas becomes a liquid is its condensation point. Now, when heat is removed from a liquid, molecules slow down until it becomes a solid. The temperatures in which each substance changes to a different state are unique properties to that substance. Did you know that water is the only substance on Earth that transforms into all three states? It is. Water boils at 100 degrees Celsius and it freezes at 0 degrees Celsius. In Lesson 1, we learned that mixtures are physical combinations of two or more substances that keep their original properties. You remember salt water from Lesson 1, right? Well, salt water is a solution or a mixture that stays the same. This particular solution includes ions and atoms of two or more substances. The substance in a solution that is dissolved is called a solute. The substance in which the solute is dissolved is the solvent. So let me give you an example. Let's look at salt water. In this case, the salt is a solute because it is a substance that is going to be dissolved. The water is the solvent, which is what is being used to dissolve the solute. As a result of these two mixtures, we now have a solution: salt water. Now that we are done with our lesson, let's move on to practice 2, found on page 555. As it is customary for the practice 2, go ahead and pause the video and complete questions 1 and 4 for practice 2. And when you are ready to review them together, just click play. So for questions 1 and 4, you are going to choose the best answer using the text from page 554. Now, let's look at question 1. Which of the following physical changes involve adding heat to a substance? Well, remember that we talked about the different states of matter and what happens in each state when you add or remove heat? Let me bring back our diagram. Here we have what happens when heat is added to liquid and when heat is added to solids. So what happens is that when heat is added to liquids, there's a boiling point. And then when heat is added to solids, there's a melting point. Therefore, our answer is A, melting and boiling. Now let's look at question 4. Water is different from most other substances. It changes from gas to liquid to solid at temperatures that are common on Earth. When it freezes, its molecules form a crystal lattice, so that its solid form is less dense than its liquid form. It is the most common solvent. Which of the following is a conclusion about water rather than a supporting statement? Let's look at our options. A, water is a unique substance on Earth. B, water changes state at temperatures typical on Earth. C, frozen water is less dense than liquid water. Or D, water is Earth's most common solvent. The answer is A. Water is a unique substance on Earth. This statement is a conclusion or a general statement that is supported by the statements that give details about the properties of water. At this time, pause the video, complete questions 2, 3, 5, and 6, and click play when you are ready to continue. Let's move on to lesson 3, chemical reactions. In a chemical reaction, the atoms or ions of a substance are rearranged to make a new product. The atoms or ions that are rearranged are called reactants. When a chemical reaction occurs, matter stays the same, and as a result, the mass of the reactants also remain the same. The concept of mass equaling the same prior to post-chemical reaction is called the law of conservation of mass. For example, let's see what happens when the atoms in iron, water, and oxygen react to each other. They form hydrated iron oxide or rust. Chemical reactions are represented by chemical equation. In a chemical equation, the reactants are shown on the left side and the products on the right side. They also show how many units of each reactant and product are being used. Due to the law of conservation of mass, the chemical equation needs to be balanced. In other words, the number of atoms of an element on the left side must equal the same number of atoms of an element on the right side. Let's look at an example. The chemical equation that represents combining of hydrogen and oxygen to yield water is the following. I'm now going to show you how to calculate chemical reactions because you know that we can't leave science without incorporating some math, right? Well, let's get started. As you can see, On the left side of the equation, we have 2 hydrogen and 2 oxygen atoms. And on the right side, we have 2 hydrogen and 1 atom. The equation is not balanced. However, if we add a 2 before the hydrogen, we now have 4 hydrogen atoms and 2 oxygen atoms. Well, it seems our oxygen atoms are now balanced. We have 2 oxygen atoms on both sides, but not our hydrogen. It's still unbalanced. Let's see if we can fix it. We are now going to add a 2 in front of the hydrogen. So let's see what happens. When we multiply the 2 times the 2 hydrogen atoms, we get 4 atoms. So now the hydrogen atoms are balanced on both sides. And that, my friends, is how we calculate chemical reactions. In this particular equation, 2 molecules of hydrogen combined with 1 molecule of oxygen form 2 molecules of hydrogen of H2O or water. The equation is now balanced because there are 4 hydrogen atoms and 2 oxygen atoms on both the right and left side. Remember that an equation can be balanced by changing the coefficient or the number before the variables, but it cannot change the subscripts, which is those little numbers right after the variables. A chemical reaction is powered by energy. There are 2 types of chemical reactions, endothermic and exothermic. In an endothermic reaction, the reactants absorb energy from their surroundings. Think when you're cooking an egg. When you add heat to the egg solidifies. The egg is absorbing the heat to cook itself. In an exothermic reaction, the energy is given off with the products, usually in the form of heat or light. So let's pretend we are camping in the woods and we need to start a fire because it's super chilly. Just be careful you are not burning wood during a no-burn day. The firewood, which is a substance, it needs an accelerant to start burning or reacting. Once the accelerant combines with the firewood, you get a reaction, which is heat and light energy. For every chemical reaction, you need an activation energy. In other words, we need to light a fire to get them going. Get it? Just kidding. Let's move on. Every chemical reaction needs a different amount of energy depending on the reactants. The graphs show the relationship between energy and time in both an endothermic and exothermic chemical reactions. Now that we have finished our lesson, let's move on to practice 3, found on page 557. At this time, pause the video to answer practice 3, questions 3 and 4. Choose the best answer for each question. Once you are ready to review them together, go ahead and click play. Let's start with question 3. Juanita would like to cook a scrambled egg on her gas stove. When she first turns on the stove's burner, the electronic ignition produces a spark that sets the gas burning. As the gas burns, it heats the frying pan. As the egg cooks, it absorbs the heat energy from the pan and solidifies it. Match the correct form of energy needed with each step of Juanita's cooking process. So let's review the different forms of energy. Activation energy is the time needed for a substance to react. The endothermic energy is the reactants absorb energy from its surrounding. And the exothermic energy gives up energy in either heat and or light. So let's look at the first step. Juanita ignites the gas. This is the activation energy because this is the amount of energy that is needed to start the reaction. In the second step, the gas burns. This is the exothermic period because the gas is giving out energy in the form of heat and light. And finally, the third step, the egg solidifies, is a perfect example of endothermic energy. The reactant is absorbing the surrounding energy. Let's move on to question 4. In the graphs on page 556, what does the horizontal axis represent? For this question, let's refer to a graphs that demonstrate the relationship between energy and time. Here you go. So let's look at our options. A, the instant the reaction starts. B, the instant the reaction stops. C, the time during which the reaction occurs. And D, the energy level in the reaction. So as you can see in the graph, the horizontal axis represents the time in which a reaction occurs. Therefore, our answer is C, the time during which the reaction occurs. At this time, pause the video, complete practice questions 1, 2, 5, and 6, and click play when you are ready to continue. Let's now move on to lesson 4, the nature of energy. Energy is defined as the capacity to do work, and work is done whenever a force is applied to an object to set it in motion. Therefore, anything can make matter move, change direction, or speed. Energy comes from many forms. It can come from heat energy, which changes a solid to a liquid or a liquid to a gas, and it's the most common in chemical reactions. Or it can come from a light energy. This one creates images causing film to react, kind of like in photography. Also, the light energy is part of a process of photosynthesis in green plants. Electrical energy is needed in order to start a motor and to store data on a hard drive. Chemical energy has multiple uses. For example, in food, it provides the energy a human being needs to survive. Chemical energy also heats building when oil, gas, coal, and wood is burned. Chemical energy is also responsible for providing electricity in batteries when they are connected to a circuit. Nuclear energy. Nuclear energy forms when the nuclei of atom breaks apart, and as a result, they provide energy to produce electricity or power submarines. Finally, mechanical energy. Mechanical energy is used to turn the axles in a car and to turn the blades in a fan. Energies can be converted from one form to another. For example, in the use of electricity in power plants, a fossil fuel or coal, which is a chemical energy, is burned to produce heat energy that turns water to steam. In return, the steam turns the blades of a turbine or a fan, producing mechanical energy. The turbine then powers the generator, which produces electrical energy. And electrical energy is used in homes to provide heat energy, light energy, sound energy, and mechanical energy. Despite energy changing in many forms, the amount of energy remains a closed system, which means that it remains the same. This is because of the law of conservation of energy. Two basic types of energy are potential energy and kinetic energy. Potential energy is the energy stored in an object, and kinetic energy is the energy that a moving object has. Let's take a look at what we mean. When you raise a hammer into the air, the hammer has potential energy because of its upswing position. When you bring the hammer down, it has kinetic energy because it's an object in motion. When the hammer makes contact with the nail, you are transferring energy from the hammer to the nail. The energy that you transfer from the hammer to the nail is equal to the work. Remember, work is the force applied to an object to set it in motion. So the energy that you transfer from the hammer to the nail is equal to the work done by the hammer onto the nail. The work can be measured in joules. On the other hand, the rate of doing the work or consuming energy is called power, and it can be measured in horsepower or watts. Many years ago, physicist Albert Einstein discovered that the relationship between energy and mass, in which energy equals mass times the speed of light, or in other words, E equals mc squared. Since the speed of light is an infinite number, the equation indicates that there is a great deal of energy in even the tiniest bit of matter. In other words, if mass is changed to energy in a nuclear bomb in nuclear power plants, the atoms will get bigger and split into two or more smaller atoms with less mass than the original large atom. Now that we have finished our lesson, let's move on to practice 4, found on page 559. At this time, take a minute to pause the video and complete practice 4, questions 1 and 4. For these questions, you are to choose the best answer. So go ahead and take a minute, and then when you're ready to review them together, just click play. Let's look at question 1. Which of the following states the law of conservation of energy? A. Potential energy is the energy of position. Kinetic energy is the energy of motion. B. Energy can be created and destroyed as well as changed in form. C. Energy cannot be created or destroyed, but can only change in form. Or D. Energy cannot be created, destroyed, or changed in form. In this lesson, we learned that energy can change its forms, but its energy amount remains the same, so it cannot be destroyed or created. Therefore, our answer is C. Now let's look at question 4. What does Einstein's equation E equals mc squared express? A. The relationship between electricity and magnetism. B. The relationship between energy and mass. C. The speed of light in a vacuum. Or D. The relationship between electrical energy and the nuclear energy. According to the passage on page 558, Einstein's equation explains how energy can be converted to mass and vice versa. Therefore, our answer is B, the relationship between energy and mass. At this time, go ahead and pause the video, complete practice questions 2, 3, 5, and 6 on your own, and then click play when you are ready to continue. Let's move on to lesson 5, motion and forces. Everything in the universe is in motion, including objects that seem to be at rest, but they are moving at the rate of the Earth's rotation. Speed is the rate at which an object moves, and velocity is its speed in a particular direction, and acceleration is the rate at which velocity changes. Let's put this into perspective. Think about a vehicle that is on the road. Let's pretend that the vehicle is going at a speed of 70 miles per hour. Well, that's the speed of a vehicle. Now, the vehicle is going to turn into a specific direction. Let's say right. But the vehicle does not slow down. It keeps going at the same speed. In this case, the combination of speed and direction, it's the velocity. What happens when a car comes to a curve? Well, in this case, the car will either have to increase or decrease the speed and change its velocity. In this case, the car will decrease the speed to 45 miles an hour while changing direction. We learned about speed, velocity, and acceleration. What about force? What is force, and where does it fit in with the other concepts? Force is anything that changes the state of rest or motion of an object. A push or a pull on an object is a force. Gravity and friction are also forces. So let's say you're standing in line and a stranger bumps into you. Well, because you were at rest, the force that the stranger transferred to you, in this case, the bump, it made you move. A long time ago, Sir Isaac Newton, an English physicist and mathematician, set specific laws about the movement of objects. These laws are called laws of motion. The first law of motion is the law of inertia. Pretty much what it states is that an object is at rest and will stay at rest until a force acts upon it. Or an object in motion will stay in motion at a constant speed in a straight line until a force acts upon it. Objects moving on Earth will slow down and stop because of friction and gravity. For example, a bullet will continue to travel in a straight line until the friction from the air slows it down and eventually gravity pulls it to the ground. The second law of motion is the law of motion or acceleration, which states that the acceleration of an object depends on its mass and the force acting upon it. The greater the force, the greater the acceleration. So the more mass an object has, the more mass or the more force it takes to move it. And if a constant force acts upon an object, the object will move with constant acceleration in the direction of the force. Let's look at a fire truck. A fire truck needs a more powerful car engine because of its mass. It takes more force to accelerate an object with more mass, and fire trucks are huge. Now let's look at the third law of motion, which is momentum, which pretty much means that for any action, there is a reaction either equal to its action or opposite to its reaction. So if you were to smile at a stranger, the reaction from the stranger can either be to smile back at you or look at you like there's something wrong with you. Huh. Let's move on. It also states the amount of energy that a moving object has, and that it's dependent on its velocity and mass. Momentum is defined as an object's mass times its velocity. So if an object is given momentum, another object must receive an equal momentum in the opposite direction. For example, when a bullet is fired out of a gun, the bullet travels forward. But the bullet's forward momentum causes the gun to recoil or move back. there was a reaction to the action. Now that we are done with our lesson, we can move on to practice 5, found on page 561. At this time, pause the video and complete practice 5, questions 4 and 5. Choose the best answer for each question. Once you are ready to review them together, just go ahead and click play. Let's look at question 4. A car is traveling at a velocity of 30 miles per hour across a narrow bridge when it is approached on a collision course by another car traveling at 30 miles per hour. The momentum of each is propelling it forward, and there is no way to completely avoid an impact. Because the momentum of the car blank, each driver should attempt to decrease his car speed to lessen the severity of the impact. The fifth paragraph on page 560 indicates that the momentum is calculated by multiplying mass and velocity. Slowing a car before a collision decreases a car's momentum. Because momentum is a measure of the energy of movement, slowing the cars will result in less energy on collision and so less damage to both cars. Therefore, our answer is A, decreases when its velocity decreases. Now let's move on to question 5. Graphs are often used to convey information about motion. One type of motion graph shows distance and time. Distance is measured from a particular starting point. If the distance graph has a straight horizontal line, the distance is unchanging and the object is not moving. If the distance graph has a straight line with an upward slope, the distance is changing at a constant rate. This means that the object is moving at a constant speed. If the distance graph is a curve, the object is accelerating or decelerating, depending on the shape of the curve. So what does the graph show for this question? A, an object that is not moving. B, an object that has a constant speed. C, an object that is accelerating. D, an object that is decelerating. The graph shows a straight line that slopes upward. According to the paragraph, this type of graph shows an object that is moving at a constant speed. Therefore, our answer is B. At this time, pause the video, complete practice questions 1 through 3 and 6, and click play when you are ready to continue. We are now moving on to lesson 6, the last lesson for this chapter, electricity and magnetism. Early on, we learned about atoms and how its electrons are either positively or negatively charged. We also learned that opposite charged electrons attract each other while equally charged electrons repel each other. Well, sometimes when electrons are pulled away from atoms, they create their own areas of positive or negative charge. This happens when two objects are rubbed together, creating static electricity. Think about a balloon and a rug. When you rub the balloon to a rug or to your hair, like I sometimes do, it creates static electricity. Static electricity differs from an electric current, which is the flow of electrons through a substance. A direct current only flows towards one direction, and it is used in battery-operated devices. An alternating current flows back and forth rapidly and is commonly used in household wiring. A conductor is a material that allows electrons to move freely from atom to atom. For example, metals. An insulator, this does not allow electrons to move freely from atom to atom. And a good example is rubber and plastic. Semiconductors, while those are substances whose ability to conduct electricity is between both the conductor and an insulator, so it doesn't know which direction to take. A good example of a semiconductor is silicon, which is used in electronic devices. An electric current produces a magnetic field that affects magnetic substances. Magnetic fields are produced by moving charged particles. Let's look at an electromagnetic, which is a type of magnet in which the magnetic field is produced by an electric current. In an electromagnetic, the charged particles move along a coil of wire connected to a battery or other power source. In a permanent magnet, the spinning of electrons create a magnetic field. And every magnet has two ends, a north and a south pole. And just like I mentioned earlier, opposites attract and like poles repel each other. Try it at home. Try to join two magnets together from the same poles and let me know if you can do it. If you are successful, you may have just made a new discovery. Just like we learned earlier that electric current produces magnetic fields, a moving magnetic field can also produce an electric current. This concept can be applied to electric motors, generators, and transformers. In electric motors, magnetic fields push against one another, turning the shaft of the motor. In generators, the moving magnetic field produces an electric current. And finally, in transformers, not the movie, not Optimus Primes or Decepticon, but the other transformers. They use an incoming electric current in coiled wire, which produces fluctuating magnetic fields, which in turn produce an outgoing electric current of a different voltage. The difference in voltage is caused by the differing sizes of the wire coils. Now that we've finished our lesson, let's move on to practice 6, found on page 563. For practice 6, we are going to complete questions 1 and 2. You are going to choose the best answer for each question. Go ahead and take a minute, and once you're ready to review them together, just click play. Let's start with question 1. Suppose a drawing of magnets with the north poles facing one another were added to the diagram on page 562. What would the new drawing show? A. Two poles attracting one another. B. Two poles repelling one another. C. Magnetic lines of force connecting the poles. D. Magnetic lines of force flowing southward. Well, according to the diagram, like poles repel. So a drawing of two north poles facing each other would look the same as the diagram of two south poles facing each other. Therefore, the answer is B, two poles repelling one another. Let's now look at question 2. What is the reason copper and aluminum are used for electrical wiring? A. Copper and aluminum are conductors. B. Copper and aluminum are insulators. C. Copper and aluminum are semiconductors. Or D. Copper and aluminum are magnetic. Well, electrical wires need to be made of something that carries electricity easily, which is what conductors do, right? Therefore, our answer is A. Copper and aluminum are conductors. At this time, pause the video, complete practice questions 3 through 6, and click play when you are ready to continue. We have finally completed Chapter 4, the last chapter in the book. This concludes the material in the GED Kaplan book. Congratulations! For the following video, we will be providing you study material to prepare you for the civics component of the GED test. The civics video is designed for any resident in the state of Arizona. For those who reside out of state, please consult your local Department of Education. For your convenience, a link will be provided in the civics video description box for additional GED requirements pertaining to your state of residence. Great job, everybody. See you soon.